All right, so now we're going to begin putting everything together. We're going to take what we were doing before, breaking down circuits and finding the total resistance of some of these more complicated circuits, and we're going to add in what we know about voltage and current to do basically a complete circuit analysis, similar to what we did with just our simple series and parallel circuits. So the general strategy here, and again, we're just applying a lot of the things that we already know, but we're first going to find the overall resistance by breaking down the circuit. Again, redrawing it, combining resistors until we have a single resistor. And then we're going to solve for the overall current. Okay, that's going to be a key step there. That's going to allow us then to go back through and solve for the voltage and current for each one. We're going to put the circuit back together is the next step. Solving for voltages and currents along the way. We will be using Ohm's law a ton during this portion because based off of our voltage and current rules, if we can just figure out one voltage or one current, we can use Ohm's law, V equals IR, to get the voltage or the current that we don't know. And we're just going to keep going, working our way back through until we have all the individual voltages and currents. Much like the last bit that we were talking about with breaking down circuits, combining them to form a single resistor, I think this is probably most easily explained by doing some example problems. So that's what we're going to do now. All right, so here's our first circuit with 4 resistors here. I'm going to start by just breaking it down and getting the overall resistance. So first combination of resistors I see here are R2 and R3. And so we're going to break them down by saying 1 over RT equals 1 over 5 plus 1 over 20. And then we find that the equivalent resistance there of 2 and 3 combined is just going to be 4 ohms. So we're going to go ahead then and we're going to redraw this circuit down below using 4 ohms instead of those 2 resistors. So we're going to have R4 still up here, which is 4 ohms. We're going to have R23, the one we just solved for, which is also 4 ohms. And then we're going to have R1 down here, which is going to be 1 ohm. And that's all connected to a 9-volt battery. Our next step, we just have a basic loop here. We can see that these are all in one giant loop. They're all in series, so to get the total resistance here, we can say 4 plus 4 plus 1, and so we get a total resistance here of 9 ohms. So that's going to be our first step here in this process, is breaking that down and finding the total resistance. Our second step is we're going to go ahead and use that total resistance to get the current leaving the battery. So I'm going to go back to Ohm's law. I'm going to say V equals IR. So 9 volts equals my current times my resistance, which is 9. And we find that the current here is just going to be 1 amp. So that means I have 1 amp of current leaving that battery and traveling through the circuit. Now what I'm going to do is I'm going to go ahead and use Ohm's law, use my voltage rules, use my current rules to go back and find the voltage and current on each individual resistor here. So that 1 amp of current leaves the battery. It's going to go through R4. It's going to go through this R23, which I realize is not an actual resistor in the circuit, but it's a combination of these two. But we'll still treat it as an actual resistor for this particular step. And then it goes through R1. So that means, because all 3 of those are connected in series, each of these resistors is going to get 1 amp of current. And then using Ohm's law, I can find the voltage on each. So I'm not going to write out Ohm's law each time, but do know that we are going back to this V equals IR time and time again here. So using Ohm's law, I can find that the voltage across this resistor would be 4 volts, right? Just 1 amp times 4 ohms. Voltage across this resistor would be 4 volts, and the voltage across this resistor would be 1 volt. I'm going to now step this back to my previous circuit, okay, the initial circuit that I had, and I'm going to relabel all the resistors here that didn't change. So both of these, R1 and R4, those were the original resistors. So we know that it's 1 amp on each. This one has 4 volts, this one has 1 volt. And now what I want to do is think about this R23. Okay, so knowing that these two are combined in parallel, they ultimately combined in parallel to create this R23 down here, which had 1 amp of current going through it and 4 volts. I know that because resistors in parallel get the same voltage, that 4 volts is actually going to be across each one of these resistors. Another way of looking at this and proving this is if I just think about a loop through this circuit here. If I go across this one, that's 4 volts, and then I go across R3 and then R1, which is 1 volt, this one must be 4 to add up to 9. And same thing if I take the other pathway, this one also must be 4, so it adds up to 9. So I can then go ahead and say that each one gets 4 volts, and that's always going to be true. When we take a combined resistor and break it back up, and they were connected in parallel, each one will get that full voltage. The current then we can find using Ohm's law. So 4 equals 5. So for the R2 we can say 4 equals I times 5. So the current there is 0.8 amps. And for R3 we can say 4 equals I times 20. So the current there is going to be 0.2 amps. All right, and so I can fill those in. So that's going to be 0.2 amps. That's going to be 0.8 amps. And this makes sense because I know that 1 amp comes in and it splits. These two currents add up to that 1 amp because that 1 amp split to go through this one, and then it comes back together to reform 1 amp. So that's the basic idea we have with some of these problems. We're taking it one step at a time. We're breaking it down into our total resistance. All right. Then we're finding our overall current, and then we're going back and doing these steps here, working backwards, all right, to find the voltage and current through each. And this is why it's really important that we're redrawing the circuit every single time. All right, for this next circuit here, I'm going to start by taking a look at the R3 and R1. We can combine those in series. So I know that my total will just be 1 plus 3, which is 4, of course. And then I'm going to redraw that circuit, okay, replacing it with that single resistor, and look for my next combination. So my new circuit, we still have 16 volts from our battery. You don't necessarily have to draw all the bars of the battery. That part doesn't really matter. We have R4 here, which is 4 ohms. We're going to now have R13 here, which is also 4 ohms. And we're going to have R2 over here, which is 2 ohms. All right, and then I go ahead, I'm going to do my next combination, which is going to be these two are combined in parallel. So I can say 1 over RT is going to be 1 over 4 plus 1 over 2. All right. And so that combines to be a total resistance here of 1.33 ohms. That's the combination of 1, 2, 3, 1, 2, and 3. And then I'm going to do my final redraw here, combining those, and I'll be left with just a simple series circuit that I can just add up. So we have our 16 volts here. We have 4 ohms here, combined with, that's for R4, combined with R123, which is 1.33 ohms, all hooked up to that 16 volt battery. And so my total resistance here, which I'm going to get just by adding up those final two resistors, is going to be 4 plus 1.33, which gives me a total resistance of 5.33 ohms. From there, I can go ahead and I can find the current that is leaving that battery. I'm going to do that by doing V equals IR. So 16 equals I times 5.33. If I didn't round it all, I'll actually get a current here of exactly 3 amps. Otherwise, you might get 2.99 or something along those lines. So that means we have 3 amps of current leaving this circuit and traveling around. I'm now going to go on to step 3 here, where I'm finding the voltage and current on each individual resistor here. So knowing that these are all connected in one big series, I know that both will get 3 amps of current here. Using Ohm's law, which we're coming back to time and time again during this process. 3 amps, 4 ohms, that means this one must be 12 volts. 3 amps, 1.33 ohms, that means this one must be 4 volts. And now we're going to step it back 1, okay? So the 3 amps and the 4 volts on R4, that was the original, or 3 amps and 12 volts, that was the original resistor, so that just steps right back to here. Nothing changes. But I do see that this R123 really came from these two connected in parallel. Because they were connected in parallel, each one will get that full voltage, 4 volts and 4 volts on each one. And then I can do Ohm's law to get the current. So V equals IR, 4 equals 2 times I. This one will get 2 amps of current. This one will get 1 amp of current, and that makes sense because those two currents should add up to the 3 amps that's coming into this junction. I'm going to then step it back one more. I see that R4 and R2, those were the original resistors, so I can say R4 is 3 amps and 12 volts. R2 is going to be 2 amps and 4 volts. All right. And you can just go back to the original, and you don't necessarily have to write it every single time like I am here. I'm just trying to reinforce the point. But what I'm going to do now is I'm going to see that this R3 and this R1 were a combination, all right here, and they were combined in series. So in parallel, they both get the same voltage. In series, they're going to get the same current. And so each one is going to get that full 1 amp from the battery. Okay, so each one gets 1 amp of current, and that really comes from the fact that we have 3 amps coming around here. 2 goes straight, the remaining 1 must go down through that branch. Then, using Ohm's law one more time, I can see that this one will be 3 volts, and this one will be 1 volt. Okay, and again, that just comes from doing Ohm's law. And so there is my circuit analysis for that one. We broke it down, found the total resistance, and then built it back up. Alright, so for this final practice problem here, same basic idea. We're going to break this circuit down and then build it back up to find the voltage and current for each resistor. So I'm going to first look for my simple combinations. So I see that R1 and R2 are connected in parallel, which means I'm going to use the 1 over equation to find that the equivalent resistance of those two is going to be 4 ohms. I'm going to do the same thing with R4 and R5. They are connected in series, so I'm just going to add those two up. And so the equivalent resistance of 4 and 5 is 24 ohms. I'm going to then take that, go ahead, redraw the circuit, and break it down from there. Alright, so I have my circuit redrawn here. So this is going to be that R12, which we found to be 4 ohms. This is R3, which is the original resistor we had in the circuit, which is 8 ohms. And then we have our R45 over here, which is 24 ohms. So the next simple combination I'm going to find here is that combination of 3 with 4, 5. They are connected in parallel, so I can say 1 over RT is going to be equal to 1 over 8 plus 1 over 24. So our equivalent resistance of 3, 4, and 5 together is going to be 6 ohms. I'm going to go ahead, redraw the circuit one more time, and then we'll start putting it back together. So for my final version of the circuit, I have this R12 up here, which is 4 ohms, and then I have my R3, 4, 5 here, which is an equivalent of 6 ohms. So I put that all together, and I get that my total resistance here, because they're connected in series, is just going to be 4 plus 6, or 10 ohms. So now I've done that first step of finding that total resistance of our circuit. Next step, I'm going to go to Ohm's law. Think about V equals IR to get the current leaving the battery. So 30 equals I times 10, which means my current here is going to be 3 amps. And so we know that 3 amps will be leaving this battery and traveling through the circuit. We can then go through and do the voltage and current on each one. I know that 3 amps, because it's connected in series, will go through both of these resistors. So I can say that this resistor will get 3 amps of current, and this resistor will also get 3 amps of current, because that's one big series. From there, I can use Ohm's law to get the voltage. So that V equals IR, current times resistance, gives me a voltage here of 12 volts and a voltage here of 18 volts. We're now going to step this back one. All right. So this R12, that was in the previous version of the circuit, so nothing has changed there. So I'm just going to say this is still 3 amps and 12 volts. But I do see that this R345 here really came from R3 and R45 being connected in parallel. Now I know that when they're in parallel, they each get that full voltage. So that means that this will get 18 volts, and this one will also get 18 volts. And I can use that then again with Ohm's law. All right, so V equals IR once again to get the current. So I would say 18 is equal to I times 8, and 18 is equal to I times 24. And so I end up getting currents here of 2.25 amps and 0.75 amps. So this one is going to be 2.25. And then the other current here is going to be 0.75 amps. And that makes sense because they should add up to 3. So now we're going to step this back one more time. Okay, and I'm going to look back at my original resistors that I have in my circuit. So first of all, that R3, that was the original resistor, so I can go ahead and say that R3 had 18 volts, and R3 also had 2.25 amps here. All right, going back to R1, that came from combining this resistor here where they were combined in parallel. Since they were combined in parallel, they each get that full voltage of the circuit. So this one is going to get 12 volts, and this one is also going to get 12 volts. And then we can solve for our current using Ohm's law. So when we solve, we find that this one is 1 amp, 12 equals I times 12, and this one is going to be 12 equals I times 6, which means this one gets 2 amps, which makes sense because that 3 amps leaving the circuit splits into 1 and 2. I then look at my last combination here, which is R4 and 5, which were combined in series to make this resistor, R4, 5. Since they were in series, they each get that full current. So each one is going to get this 0.75 amps of current. And from there, I can use that to get the voltage on each one. So that's 0.75 amps, that's 0.75 amps. And then the voltage is going to be that current there times my resistance. All right, so I say 0.75 times 19 means that this one will get 14.25 volts, and the 0.75 times 5 means that this one will get 3.75 volts, which adds up to 18 as it should. And so there is that full problem. Again, we're breaking it down, finding the total current, and then we build it on back up.